So we're going to do a notebook walkthrough of this blog post by Philip. This blog post is fine-tuning a large language model of FLAN T5 XXL, 11 billion parameters. It's a very large model. We're going to use LoRA as the way of fine-tuning it. This is a very efficient way. As you're going to see, we're going to not need a lot of compute resources to do this. We're going to run this blog post in Google Colab. Philip's an AWS guy. I like Google Colab, so we're going to do this here. When we set up our runtime here, because of the larger size of the model, I'm going to select the largest size of GPU that we have, and we'll take a look at exactly what size GPU we have as we walk through the notebook. We'll go through all the different steps he has in his notebook. Let's jump into it. First thing is, let me just kind of let you know exactly what type of GPU I have. So I have one of the A100s here, has quite a bit of GPU memory, more than I'll need for this one, but I'd rather just go with that one. When I tried running this notebook with a smaller GPU, I had crashes for a while. So let's hope this works. Now, we're going to load the libraries. Philip's already pinned specific versions. I'm going to leave those as such here. The dataset here is SamSum, which is a dataset that's widely used for summarization, which starts with longer conversations that are then summarized down. Philip's had this in a bunch of his blog posts. I'm not going to spend a lot of time on kind of walking through this dataset. If you're not familiar with it, take some time, play around with it. One of the things I did with this dataset was actually pare down the amount of train to a much smaller size, then started working with it and getting a sense of like what the data is like. First thing we're going to do is go ahead and load the tokenizer for that. Before we start training, what we're going to want to do is pre-process our data. These scripts just find what's the largest length of the sequence length, so that way we can do it, which usually in this case, because it's a large data set, maxes out at the 2. Next, we'll go ahead and do a little bit of pre-processing, add that prefix of summarization, do all the tokenization, the padding as well. Pretty standard process for fine-tuning any type of model here that we're doing. There's nothing novel that. At this point, we're going to start loading the model. This model originally started with the FLAN T5 XXL, which was over 40 gigs in weight. That was a floating point 32. The initial version Philip used here, he brought it down to a floating point 16, which kind of have that weight. The next thing that we're taking advantage of here is bits and bytes integration into transformers, so we can work with a version that's integer 8. So again, going from floating point 16 down to int 8, it's going to save us a lot of reduced memory by about 4 times. The next step is using the low rank adaptation training, which is going to use the PEFT library that's in Hugging Face. If you want more details, on PEFT, you can take a look at the blog post that talks all about it, including its integration into Hugging Face. For my simple mind, the way I like to think about kind of what LoRA does is it takes the full matrix of weights of our models, and then it does a decomposition. So kind of, you can think of it like SVD or PCA, just finds a way to condense down and just get the essential parts of those weights. Those weights are then infused into the model. And in this case, those weights end up being, you can see down here, like less than 1% compared to all the original weights. And what we're going to do now is all we're going to do is just train that set of weights. And here's the magic. It actually works and gets us good performance. But then we can almost pull that set of weights out, take that somewhere else. This is where you'll see this same approach used with diffusers and stable diffusion as a flexible way to kind of go between models. All right, so let's move down here. We're going to go ahead and kind of do the data collector, make sure the padding is entirely set up. The last piece here is set the hyperparameters that we want for the model. I'm looking here, nothing really kind of big sticks out at me that we need to focus on here. Again, you'll play with this yourself, and let's go ahead and start training the model. Woohoo! All right, so the model training has started. This training does take a little while. You'll see here the training time here is about 9 hours to go. So it's a long time, but trust me, if you are fine tuning, as we'll talk about at the end, the entire model, it would take much more, it'd take much longer, much more resources. But still, we're working with very large size models. You can't expect it to be done as quick. Now, for comparison, the 10 hours that it takes for this particular model costs probably something on the order of like $13 if you were going to use AWS resources to do it. But if you compare that to the original post where they fine-tuned Flan T5 that took 8 A100s, over $300. Take a look at that original blog post. I've got it right here, where you can see the results and experiments when you're trying to fine-tune these very large models on different GPUs. What are the trade-offs there? But this approach of using PEFT and using low rank optimization is going to be a lot quicker. That 10 hours of training time is just way too much for me. Luckily, we have a version of the model that's fully trained. I want to just show you what that looks like. You can see here the adapter changing those weights. Remember, we're only changing a little bit of the model. We can capture that change that we've done. We've saved that over here. I can take a look at the model card, look at the results here. And what I'm going to do is I'm going to grab this model, show you how the rest of the notebook works, just so I can get this all done tonight instead of working on it tomorrow. All right, so we've added in Philip's model. We're just going to pull that down from the hub, and then we'll run the last little bit of inference on this model. So now we've got this new model loaded. Let's go ahead and just look at a random sample to see how well the predictions work. So we can see a bit of dialogue here, getting the summary. Looks fairly good on this one. Now, what we're going to do next is just go ahead and you run and get a metric, the Rouge score on this. Look at this. He even put here, recall-oriented understudy for gisting evaluation. For those of you not that familiar and want to deep dive into this, we can go ahead and evaluate the model against all the data sets, see how well we do. And again, right, what you'd always do is you'd want to fine-tune for your own task. Might not be exactly this summarization, but then at the end of the day, once you've got that through, you're going to want to evaluate that. And the code walks us all the way through that. This is going to take about 45 minutes to run through the evaluation. Again, we're working with large data sets and large models. But the big takeaway is using this. It's a lot quicker, a lot more efficient than just fine-tuning the entire model. And you know what? This way actually gives us a bit more accuracy as well. So I appreciate your time watching this. I'm not an expert in all this, but hopefully I was able to at least convey this in an interesting way and get you excited to try this out.